So this is our first lecture video for Chapter 18 on electrochemistry. Now I don't know if you've ever pulled back those magazines in the back of an airplane where they sell you all kinds of stuff and they're really like overpriced. But one of the things in there is this tarnish remover. So if you've got any kind of antique silver or something like that and it's got a lot of tarnish on it, you can buy this product and it actually works really well. So you've got this little plate of metal here and you have this packet of activator. And when you add this activator to it, you just simply dip your silver into the water with the activator in it and set it on top of this metal plate, and it removes the tarnish from the silver, and it works really well. The thing is, it's $20. And if you know anything about electrochemistry, you know that this is way overpriced for what you're actually getting. Because in truth, that activator that they add, that white powder, is simply sodium bicarbonate, which is baking soda. And this plate here that you have, this metal plate here, is actually a sheet of aluminum. So you can do the exact same thing with a sheet of aluminum foil and a box of baking soda for a fraction of the cost. So this is one of the reasons why we want to teach you about different aspects of chemistry. First of all, so you don't get taken advantage of, but also so you can better understand some of the processes that happen around you on a daily basis. Okay, so we're going to start off by looking at redox reactions. And this should be a good review of some of the things that you talked about in your Chem 1A course. So one or more elements change oxidation numbers in a redox reaction. So something's being reduced and something's being oxidized. And all single displacement and combustion reactions are redox reactions, and some synthesis and some decompositions. And these reactions always have both an oxidation half and a reduction half or portion to it. And we oftentimes split these reactions into their half reactions, so the oxidation portion and the reduction portion, so we can understand what happens. So during these redox reactions where one thing is oxidized and another thing gets reduced, this is why we write half reactions so that we can see the electrons being transferred between the two. Now the oxidizing agent is a reactant molecule that causes oxidation, and it contains the element that's reduced. And the reducing agent is a reactant molecule that causes reduction. So it itself does not get reduced, it causes something else to be reduced. So since it reduces something else, it itself gets oxidized. And just a reminder, so oxidation is the process that occurs when the oxidation number of an element increases. So that element is going to lose electrons, and that may be a result of the compound adding oxygen or losing hydrogen. And the half reaction has electrons as products. So if it's oxidized, the oxidation number is going to increase, so it's going to be losing those electrons, so the electrons are going to be a product. And in the reduction, that's when the oxidation number of an element decreases. So this is where they get the term reduction. The oxidation number decreases. So for the oxidation number to decrease, to gain electrons. So the element gains electrons and the compound loses oxygen, or the compound gains hydrogen. So in these half reactions, the reduction half reactions, the electrons are the reactants. Now some people have different ways of different mnemonics for remembering oxidation and reduction. I personally prefer oil rig, where oxidation is loss of electrons and reduction is gain of electrons. But some people use the Leo the Lion says GER. So use whatever works best for you. Now just a reminder of some of your rules for assigning oxidation states. There are a list of rules that are listed in order of priority, so you have to follow the first rule first, and then you can follow the other rules. But our first rule is free elements have an oxidation state of 0. So for instance, sodium metal would just be 0, and then chlorine gas, which is a neutral diatomic, the chlorine has to be neutral as well. And then the monoatomic ions have an oxidation number equal to their charge. So sodium is a +1 ion, so it also has a +1 oxidation state. Number 3, the sum of the oxidation states of all the atoms in a compound is 0. So in a compound, the overall charge is 0, so everything has to add up to 0, so all the oxidation states have to add up to 0 as well. So if we're looking at sodium chloride, sodium ion has a +1 charge, the chloride has a -1 charge, so the overall charge for sodium chloride is +1 plus a -1, which equals 0. Rule number 4, the sum of the oxidation states of the atoms in a polyatomic ion equals the charge of the ion. So if we're talking about nitrate, here the nitrogen has a +5 charge, the oxygen has a -2 charge, so the overall charge is -1. So let's see that again. So 5 for the nitrogen, there are 3 oxygens that each have a -2 charge. So +5 minus 6 equals a -1, and that equals a -1 charge on the nitrate. Rule number 5, the group 1 metal ions have an oxidation state of +1 in all of their compounds. So for instance, sodium is a +1. The group 2 metal ions have a +2, so magnesium would be a +2 in magnesium chloride. And then the 7th rule, in the compounds, the nonmetals have oxidation states according to the table below. And the ones that are higher up on the table have the greatest priority. So fluorine would have a -1. So an example, if we're looking at tetrafluorocarbon, each fluorine has a -1 charge, which makes a carbon a +4. Hydrogen has a +1 oxidation state unless it's bound to a metal. So for example, in methane, each hydrogen is a +4, that makes the carbon a -4. And then oxygen is a -2. So for example, in carbon dioxide, each oxygen is -2, so that makes the carbon a +4. And then the group 7A, so the halogens, are -1. Group 6A, so this would be the chalcogens, would be -2. And then the nitrogen group, so the pycnitogens, would have a -3 charge. So remember, all of this should be a review from your Chem 1A as how to assign the oxidation states. So again, oxidation occurs when an atom's oxidation state increases during reaction. So oxidation is loss of electrons. So oxidation is loss, so that's where we get the oil rig. And reduction occurs when an atom's oxidation state decreases during a reaction. So reduction is gain of electrons. So if we're looking at this reaction here with methane combusting and combining with oxygen, we get carbon dioxide and water. So in this reaction, we want to assign the oxidation state so we can figure out what's being oxidized and what's being reduced. So we said that the hydrogen is a +1 unless it's bound to a metal, so each of those hydrogens add up to a total of +4. So that means the carbon has to be a -4. So each hydrogen is a +1. And then the oxygen, there's 2 of them there, it has to add up to 0, so 2 times X equals 0, so the oxygen has to be 0. The oxygen here is a -2, which makes the carbon here a +4. And the oxygen here is a -2, and each hydrogen is a +1. So then I need to start looking to see what got oxidized and what got reduced. So the carbon here went from a -4 to a +4, so that's an increase in the oxidation number. So that says that the carbon was oxidized. And the oxygen went from a 0 to a -2, so that got reduced. So here I just have the oxidation numbers written out nice and neatly below. So the carbon was oxidized as it went from a -4 to a +4. The oxygen was reduced since it went from a 0 to a -2, so it had to gain some electrons. Now the oxidation and reduction reactions, those have to occur simultaneously. So if an atom loses electrons, something else must take them. So let's look at this reaction here where we're looking at sodium metal combining with chlorine gas to make sodium chloride. Now, the reactant that reduces an element in another reactant, we said that's a reducing agent. So the reducing agent contains the element that's oxidized. And the reactant that oxidizes an element in another reactant is called the oxidizing agent. And the oxidizing agent contains the element that is reduced. So in this case, sodium is oxidized. So let's just look at the oxidation number. So sodium is a 0 here, and on this side of the equation it's a +1. And the chlorine here is a 0, and on this side it's a -1. So the sodium is oxidized and the chlorine is reduced because it goes from 0 to -1. So if sodium is oxidized, that makes sodium the reducing agent. And because chlorine is reduced, that makes the chlorine gas, so the Cl2, the oxidizing agent. So this is my oxidizing agent, and this is my reducing agent. So here would be a good time to stop the video and practice writing the oxidation numbers for each of these reactants and identifying which one's the oxidizing agent and which one's the reducing agent. So if we're looking at the first reaction where we've got hydrogen sulfide reacting with nitric acid, and it produces sulfur and NO and water, we assign the oxidation state. So the hydrogen is a +1, the sulfur is a -2. Here the oxygen is a -2, so -2 times 3 is a -6, and we have an overall -1 charge. So that must mean that the nitrogen is +5, so you have to solve for that. So if you don't remember how to do that, if I don't know what nitrogen is, I can just put a variable x, and there are 3 -2's for the oxygens, and that has to equal a -1. Then I just solve for the algebra to find out what x is, and x is +5. And then the proton here that has a +1 charge, that must mean the hydrogen is a +1. The sulfur is neutral, so it has to have a 0 oxidation state. Here the oxygen is -2, and they have to add up to the overall charge of 0, so that must mean that nitrogen's +2. And the oxygen's a -2, and the hydrogen each is a +1. So in this case, the sulfur was oxidized, so that number increased. And the nitrogen was reduced because that oxidation number got lower. So that makes the hydrogen sulfide the reducing agent because it itself got oxidized. And the oxidizing agent is the nitrate ion because it itself got reduced. So let's try another reaction. So the manganese dioxide reacting with HBr. So the manganese starts off in a +4 and it goes to a +2. And the oxygen, so it's a -2 here and a -2 here, so the oxidation number of the oxygen doesn't change. Oxidation number of the hydrogen doesn't change, it's +1 and +1. But the bromine goes from -1 to 0. So the bromine gets oxidized because its oxidation number increased, but the manganese got reduced because its oxidation number is lower. So if the manganese dioxide was reduced, that means it has to be our oxidizing agent. And if the HBr got oxidized, that means it has to be the reducing agent. Okay. Now these are just a common list of oxidizing agents. Now I took this from the publisher, and one of the things that you should notice or recognize about this, even though like some of these ions, they have the charge and then the magnitude of that charge, so rather than doing a -2, it should really be a 2-. So they actually made a mistake, and I can't easily go in and change this. So like the SO3 should be a 2- instead of a -2. So one of the things I hope that you recognize from this list of common oxidizing agents, especially down here with these manganese complexes and these chromium complexes, these are metals in high oxidation states. So if they're in high oxidation states, they're going to want to likely get reduced. So if they're going to get reduced, that means they're going to oxidize something else, so they're going to be good oxidizing agents. So oxygen and hydrogen peroxide are good oxidizing agents. Fluorine, chlorine, and bromine iodide, those halogens are good oxidizing agents because they want to take electrons, so they want to get reduced, become negative charges themselves. So they're going to take electrons from something else. So notice that when these halogens get reduced, so when they oxidize something else, notice they become a -1 charge, a 1- charge. Now in this slide, we're looking at common reducing agents. So hydrogen is a common reducing agent. So the hydrogen, when it itself gets oxidized and it reduces something else, it gives up its electron to something else, it becomes a proton, so an H+. Hydrogen peroxide can also act as a reducing agent. The iodine can become a reducing agent, so it goes from an iodine, so an iodide, so -1 to an I2. Or some of these other metals can go from like the +2 to a +3. So it itself got oxidized, but it was reducing something else. Now, the next thing we want to look at is balancing redox reactions. And this typically gives students a lot of problems because it's a long and tedious process. So expect to take a whole page or half a page at least to balance a redox reaction. And if you memorize the steps, then balancing redox reactions aren't so bad. You just have to be very careful when you write your reactions and not to make a clerical error in memorizing these steps that we give you. So the first thing that you have to do is you have to assign the oxidation numbers. So you assign the oxidation numbers so that you know what is being oxidized and what's being reduced. Your second thing is to then separate the reaction into its half reaction. So separate one reaction as the oxidation and then write the reduction reaction as a separate reaction. Then we want to balance the half reactions by mass. So the first part of doing that is balance everything except the oxygens and the hydrogens. Then once you balance everything except the oxygens and the hydrogens, balance the oxygens by adding water where you need to. And then you balance the hydrogens by adding protons, so H+. Now, if the reaction is done in basic solution, so they'll add that part to the question. So if it's done in basic solution, you need to add a separate step. Then you neutralize any protons with hydroxides in basic solutions. Then after you balance everything by mass, so by the atoms, then you want to balance the half reactions by charge. So you balance the charge by adding electrons. The next step is you want to balance the number of electrons between the half reactions. So if the oxidation reaction is transferring 2 and the reduction is only transferring 1, then you have to multiply by 2 so that you have 2 electrons being given up and 2 electrons being received. Then after you've balanced the number of electrons between the half reactions, you need to add the 2 half reactions together so that you get just one reaction. And then lastly, you want to double check yourself to make sure everything makes sense. So we're going to show you how this process works by looking at and balancing the reaction where I- reacts with MnO4 to make I2 and the manganese dioxide. And remember, this is going to be in basic solution, so we have to make sure we add this last step. Because if they said this was done in acidic solution, we would just stop at 3C and not do D and then go on to 4. But since they tell us this is in basic solution, we can't have any free protons. Okay, so remember, our first step is to assign the oxidation states. So the I-, so that's a -1, goes to I2, so that's a 0. So that itself gets oxidized. And the manganese goes from a +7 to a +4, so it gets reduced. So let's just show what those oxidation numbers are on top. So we go from I-, so -1, to a 0. So that's being oxidized. And the manganese is being reduced, going from +7 to +4. So I now need to separate the reactions into half reactions. So I'm going to write what was being oxidized and what was being reduced. Okay, now that I've separated things into my half reactions, I need to start balancing the non-hydrogen and non-oxygen atoms. So I'm just transferring this so I give myself a little bit of space, but this is exactly the same thing that was written on the previous slide. Okay, so I needed to put a 2 in front of the I minus so that I have 2 iodines on both sides. And there aren't any hydrogens or oxygens, so I don't have to worry about that. Now in the next reaction, my reduction reaction, the manganese are both balanced, so I don't have to do anything there. But I do need to balance the oxygens. So I have to balance the oxygens by adding water. So since there are 4 oxygens here and 2 oxygens here, I have to add 2 water so that I get a total of 4 oxygens on both sides. So now my manganese are both balanced, my oxygens are balanced, but notice my hydrogens are not. So I've got 4 hydrogens on this side, none on the reactant side, so I have to add 4 protons so that my hydrogens balance. Okay, so I've added my 4 protons so that all of my elements balance. I have 4 hydrogens, 4 oxygens, and 1 manganese on both sides. So I've balanced everything according to their atoms in my oxidation half reaction and my reduction half reaction. So now I've got to remember, we said this was in basic solution, so I can't have any protons. So to neutralize that acid, I'm going to add 4 equivalents of hydroxide. So there's 4 protons, I need to add 4 hydroxides. And what I do to one side of the reaction, I have to do to another. So here I've just added 4 hydroxides to both sides. Now, to clean this up, 4 hydroxides and 4 protons make 4 waters. So this is what this second line is doing. I'm just taking this line right here and writing it more simply. So I've got the 4 waters, I've just combined the 4 protons and the 4 hydroxides to make these 4 waters. Now I want to reduce this even more because now I have 4 waters on this side, 2 waters on this side. So since I have the same thing on both sides, I can subtract out 2 waters from both sides. So those cancel out, so I get a total of 2 waters on the reactant side. So now this is my final balanced equation for my reduction half reaction. So other than the electrons here, this is exactly what I had written on the previous slide. But I need to balance out the charges. So if this has an overall 2 minus charge and this one was 0, I have to add 2 electrons so the charges are balanced on both sides. And previously, before we added these electrons, there was a -1 here and a 4 minus on this side. So to make the charges balance, I have to add a 3 minus on this side by adding 3 electrons. So if in effect I balance the charges on both sides by adding electrons. So now I need to make sure that if 3 electrons are being consumed in this one and 2 are being produced by this reaction, I need to have these have the same number. So what I'm going to do is multiply this reaction by 2 so that I have 6 electrons being used. And in this reaction I'm going to multiply everything by 3 so it produces 6 electrons. So I multiply the top oxidation number by 3, the reduction by 2. So this gives me these 2 reactions right here. Now because I've written it like this, the 6 electrons on the product side and the 6 electrons on the reactant side, when I add these 2 together, will cancel out with each other. So I simply have to add my 2 half reactions now that all the atoms are balanced and all the charges are balanced, and then we have the same number of electrons being transferred between the 2. Okay, so I've just taken these 2 reactions from the previous slide and moved them up the top so everything will be a little bit more clearly. But I simply add these 2 together. So if 6i is on the reactant side, so 6i, and the 2MnO4, so that's on the reactant side, and the 4 waters. And then the 6 electrons are going to cancel out with each other, and that's going to give me 3i2 and the 2MnO2 and then the 8 hydroxides. So this is our balanced redox reaction. So notice this kind of took us a while. There are a lot of different steps, so you can see how it'd be easy to make a mistake. So don't be afraid to take a whole sheet of paper or half sheet of paper to write out this, and be careful when you write things out and be very neat so that you don't make an error. Okay, so we're just going to double check everything, and we have an elements I, manganese, oxygen, hydrogen. So we've got 6 on both sides. We've got 2 manganese on both sides. We've got 12 oxygens on both sides and 8 hydrogens on both sides. And so all the atoms are balanced, but the charges also have to balance. So on the reactant side, there's a -8 charge. On the product side, it's a -8. So in that case, everything is good. So that's the end of our first video for electrochemistry, and in the next video we'll start looking at electrical current.